Start the session. So first, I would like to introduce our speaker. Uh, Today, we have a distinct honor of welcoming a truly distinguished researcher, Dr. Snehasis Mukherjee. He is an associate professor in the Department of Computer Science and Engineering at Shiv Nadar Institute of Eminence, Delhi NCR. His academic and research journey is incredibly inspiring. He earned his PhD in computer science from the Indian Statistical Institute, one of the most prestigious institutions for quantitative sciences in the country. Following that, he broadened his international experience as a postdoctoral fellow at the renowned National Institute of Standards and Technology in US. His leadership in the field is further demonstrated by his role as an associate editor for the Springer Journal of SN Computer Science and by his experience of chairing many sessions at major global conferences. Today, Dr. Mukherjee will be speaking on the topic of engineering on supervised network for training with less data. This is one of the most critical and exciting challenges in modern artificial intelligence. As we see AI models grow larger, the demand for massive datasets becomes a major bottleneck. Dr. Mukherjee's work addresses this head on, exploring how we can build powerful and efficient AI without being data hungry. This is a topic of immense practical and theoretical importance for the next generation of engineers and researchers. We are incredibly fortunate to hear directly from an expert who is actively shaping this field. Please join me in giving a warm virtual welcome to Dr. Snehasis Mukherjee. Sir, the stage is all yours. Sir, we can't hear you. Is it now? Can you unmute, sir? Oh. So from our side, it is showing that you are unmuted, but your voice isn't coming through.
Hello, am I audible?
Yes.
Sir, it shows that you have like your mic is on, it's just your voice is not coming through. Can you check your laptop's mic option? Like there is a button there, F8.
Yes.
Hello.
Yes, so now we can hear you.
Okay, good. So sorry for the delay. Let me first. First of all, thank you for Krish and for the nice introduction, and thanks to PICT team, ACM chapter, for inviting me. So I'm sharing the slides first. Is it visible?
Yes, sir.
The slide is visible, right? It is
Yes.
moving.
Yes, sir.
Okay, thank you. Okay, so good afternoon to all of you. So today my topic is engineering on supervised network for training with less data. As we all know that for supervised learning, we need more data for training. Any deep learning models, we need a huge amount of data, and especially for image data, because I work mainly on images. So for image data, it needs a lot of images. And in many applications, it is very difficult to find out those many images. Say, for example, for medical images, if we take an example of uh, brain tumor detection from MRI images. So for applying any machine learning technique, you need to get uh, plenty of images with brain tumor and plenty of images without brain tumor to train the model, right? Which is very difficult to get in real life. So nowadays, many researchers are working in the area of uh, working with or training a supervised model with less number of training data. So there are so many approaches for them. So we'll come into that. So before starting, so this is just a thanks to my PhD student. I mean, most of the today's talk is taken from the PhD thesis of Jaideep Kishore. So he completed his PhD last year. Okay, so these are my research areas where I work: human activity recognition, egocentric activity analysis, video or image quality enhancement. So given a degraded image or video, can we enhance the quality of the image? That is one thing. Continual learning or incremental learning. What is that? So continual learning means, suppose you want to apply some model on some specific data set, right? Or suppose a specific kind of data. If I give you a quick example, suppose you want to build a model for human action recognition, right? Now you train your model with a data set where the there are lots of challenges in the data set. Say, for example, in many cases, the performers are occluded. In many cases, the performers are, say, uh, I mean, they are not in full body shape, right? And many body parts are not visible. So these are some, you can say, challenges in your data set. Now you train your model with those challenges. Now, if you apply the same model on some data where the person is fully visible, but the person appears at a distance from the camera, so that the person appears very small in the video. Now, in that case, your model may fail, right? So these are called model drift. So your model is working in some environment, but if you change the environment, then your model will fail. So in these kind of cases, one idea is that you train your model for one task, right? Task one. Now you train the same trained model on another task, say task two, right? So whatever classifier you built by training on task one, that will be again fine-tuned for class two during the second training, right? Now, after this fine-tuning process, the classifier will change a little bit, right? Now, if you apply the same model on the first task again, then the performance will drop. So this is called catastrophic forgetting. So it's just like you are studying mathematics and then you studied physics. And after you completed your physics study, again, a simple, say, mathematical problem was given to you from the chapter, whatever you studied before, and you are not able to do that. Okay, so this is catastrophic forgetting. Now, to avoid this situation, some approaches are coming up, which are called continual learning. So in this approach, what people do, you first train for the task one, and then you train the same model for task two. Okay. While training for task two, you use the learned knowledge from task one, and you update your model with the knowledge from task one while training for task two, so that it don't forget. It's just like you are studying science after studying mathematics, but sometimes one or two problems you are solving in mathematics also, right? So that you don't forget, right? So this is called task incremental learning or task continual learning. Okay? Another can be, say, class incremental learning. Class incremental learning means your model is trained for, say, cat and dog images, right? So you trained your model to differentiate between cat and dog images. Now, a new category of animal came, that is cow. Now, can you apply the same model to determine the new animal, that is cow, right? That is class incremental learning. Okay, so this is another area that we are working on. Another is domain adaptation. You are, the idea is quite same, but not exactly same. So you trained your model on one domain. Say, for example, you want to clear some hazy images, right? Now you trained your model on some hazy images and you want to produce the clear images. So you trained on some hazy image data and you build your model, right? Now you want to use the same model for another image enhancement task. Say, for example, de-raining. Okay, from raining image, you want to just strike out the rain drops, right? And make a clear image. Now, in those cases, your learned model will fail. So you have to train on the new task. That is the de-raining example, right? Now, can we make the same model adapted to the new domain, right? That is domain or adaptation. The idea is quite same in the sense that while training on the new domain, you take the you apply the learned knowledge from the task 1 or domain 1, right? While training for domain 2. Okay, so this is domain adaptation. And domain generalization is a, you can say, a one step ahead of this. So instead of task or domain 1 and domain 2, if you think of a series of domain, first you train your model on one domain, then train your model on another domain, then another domain, and so on, just to make your model robust for any kind of tasks like this. Say, for example, you want to make a an autonomous vehicle, right? Now, the autonomous vehicle should work, the video should work on all kinds of adverse situations or adverse weather conditions, right? Say, for example, if the environment is hazy, then also it should work. It should produce the clear image. If it is raining, then also it should work. If it is snowing, then also it should work. Or if it is blurring, then also it should work. Okay. So making the same model adapted to many domains, right? So this is another area that is coming up. And today's topic is more towards neural architecture search. So finding out a neural network specific to a given task, right? So this is just a basic knowledge about supervised and or different learning strategies. First of all, supervised learning means the labels are given with the data. You want to differentiate between cat and dog images. So in that case, while training, you train the system with some cat images, some dog images, and all the cat images are marked with cat. All the dog images are marked with dog, and you train the system with that. So that is supervised learning, right? And unsupervised learning means you are not giving the labeled information. You have cat images, you have dog images, but they are not labeled. Which one is cat, which one is dog, you are not giving to the system, right? Now the system will analyze all the features and come up with some solution that, okay, these set of images are one category, these set of images are another category, like that. That is unsupervised learning. Reinforcement learning means you learn from your mistakes. A robot is navigating, right? Suppose this is an example. Suppose you train your robot to go ahead, move left, move right, and all these things. Now, if some obstacle comes in the front, first time it will get stuck with the obstacle. But next time, whenever another obstacle will come, it will try to avoid it, right? So that is reinforcement learning. And for all these tasks, one thing you have to do, that is learn good features, right? Say, for example, for distinguishing cat and dog images, if your features are like number of eyes, that is not a useful feature, right? Number of eyes are same for cat and dog. That is 2. Number of tails, that is same. Number of legs, that is same for cats and dog. But if you say consider a feature like size of the animal, okay, then it may be a good feature in most of the cases, because most of the dog breeds are larger in size than cat, right? So so that is why good features are very much important in any machine learning tasks. Here are some challenges in supervised learning methods and some possible techniques or solutions that I have mentioned. First of all, requires a huge amount of data for training. That is the main disadvantage in supervised learning methods. A possible solution may be transfer learning. What is transfer learning? Suppose you train your, so suppose you want to apply your model, on some area where it is very difficult to get a sufficient number of images for training, right? Suppose you want to classify bird images and you don't get sufficient number of bird images, right? Then what you will do, you first train your model on some other area, other domain, where huge amount of data is easier to get, say image classification. So lots of data are available. Now you train your model on that. Now you apply the trained knowledge on the specific task, distinguishing the bird, right? So you train your model and fine tune your model on the target data, right? That is called transfer learning. Second is annotate a, now in transfer learning, there are so many problems. I mean, a bigger problem is that in most of the cases, the same model is not fit for the target domain. Okay, that is a very common problem in transfer learning. Annotate a huge data for training needs a lot of manual effort, right? So this is another problem in supervised learning. One possible solution may be self-supervised learning. What is self-supervised learning? Suppose you you want to distinguish between cat and dog, right? Now, instead of saying this is cat and this is dog, what you are doing is that this and this image are same. This and this image are different, right? So you are training the model with the similarity. Which images are similar and which images are different. Okay, so that is self-supervised learning. It is based upon contrastive learning method. So it actually learns the contrast. Okay, so by the way, you can stop me and ask any question if you want, if any doubt is there. Okay.
If you guys have any doubts, you can just raise your hand and we will unmute you to ask them.
Yes, yes. Okay. Another problem may be redundant data. Suppose we all know that for image classification, we need a huge amount of data. Now you collect as many data as possible, right? And make a collection to build the data set for training. Now the problem is that there will be many images which are of similar kind. Now, if you train your model with these images, so your model will learn anything new from these extra set of images, right? Now, can we come up with a system where we can train the model with a lesser amount of data, right? But the efficiency after training will be the same. Efficiency of your classifier will be the same. So one possible solution may be dataset condensation. You condense the dataset. Suppose you have for image classification, you have a dataset with 50,000 images, right? Now, if now you somehow you learn the dataset, the nature of the dataset and nature or the distribution of different classes, you come up with another set of data which contains only say 40,000 images, but these 40,000 images are good enough for any model, CNN model, say for example, to achieve the same kind of efficiency with 50,000 data. Now, these images, whatever you get now, they may not be meaningful on your eyes. Maybe suppose you are distinguishing between different kind of animals, right? Cat, dog, cow, and there are several other animals, right? You want to distinguish between images. Now, after data condensation, you have plenty of images of cats, plenty of images of dogs, and so on. Now, you after condensation, you get a lesser number of images where cat images are also there, dog images are also there. But if you just pick up any cat image, then you may not appreciate it. Okay, so it may not look like a cat, what you think. But from machine learning perspective, for training the model, the useful features are all there in the cat image, right? So this is dataset condensation. Another is, so dataset condensation is nothing but making a smaller dataset. Another problem in supervised learning, that is reducing the number of required training data. A possible solution may be active learning. What is active learning actually? Suppose you have, so this active learning is different from continual learning that we just discussed before. Okay. Active learning means, suppose you have a problem of image classification, right? Now you have a data set with 50,000 images, all are annotated. Now, in supervised learning, you train the whole, you use the whole data set of 50,000 images to train your model, right? In active learning, what you will do, you'll start with training. You first start training with 10,000 images, not all the 50,000. You just use 10,000 images for training. You will get some classifier. Obviously, this classifier will not be great like whatever you get after training with 50,000 data, right? But with this model, you try to predict the classes of the other data, other images, right? And also you try to make it, you try to calculate some confidence score. How confident you are, how confident the model is to recognize it as a dog. How confident is the model to recognize this as a cat image, and so on, right? Now, with this confidence score, can we come up with an algorithm that we can select a next set of 5,000 images for training so that these 5,000 images will be good enough to train the model with, right? So instead of taking the whole data set, after 10,000, you are again taking 5,000 more images based on this scores, the confidence scores, how confidently your model is detecting them. Now you trained with 15,000 images. Your classifier will be better than 10,000. Again, do the same thing. Again, try to predict the classes of the remaining data. Score them. And based on the score, again take 5,000 more images for training, and so on. So in this process, we'll see that instead of taking 50,000 images, if you just use 35 or 40,000 images, then also you can achieve the same level of accuracy, whatever you get after training with 50,000 images. Okay, so this is the idea of active learning. Okay, so these are some active area of research where research is going on currently. And if I am not wrong, the future research direction will be a combination of any of these. Okay. Yes. Any question?
No, sir.
Okay. Okay. Now let us come back to whatever is today's topic now. So why NAS? First of all, neural architecture search. The idea is that find a suitable network specific to a given task. Suppose you want to, yes, Shreya, you have a question?
Yes, sir. Sir, I have a question like how can we identify whether our model has truly learned the pattern or is it just memorizing the values as the data is limited?
Yeah, that is a good question. So in any supervised learning method, the goal is that your model must be generalized. What is the meaning of generalized or generalization? Generalization means your model should be able to predict any unknown data of any class. Suppose if you train with a set of data, say cat images, now for testing, you will not give the same set of cat images. You will give a different set of cat images to test, so that you will make it will make the model clear that it is actually not memorizing, right? So did it answer your question? Or?
Okay, so yes, sir.
Okay, okay. Okay. So the main goal of NAS is that finding a suitable network specific to a given task. Okay. Given a task where maybe getting a number of training data is very difficult. So for that particular task, how can we come up with a neural network, suitable neural network? Currently, most of the cases, the researchers come up with some heuristics that, okay, according to their own, say, experience, they used to find out, okay, these kind of data set, these kind of architecture will work. But there is no specific rule for that, right? Now, manually checking all possible hyperparameter values. By the way, what is hyperparameters? Hyperparameter means, say, for example, you have a neural network. Now, what will be the number of layers of neurons? That is a hyperparameter. What will be the number of neurons in a given layer? That is another hyperparameter. What will be the learning rate? That is another hyperparameter. Okay, so there are several hyperparameters for any neural network. Now, you are fixing a neural network means you are actually fixing the hyperparameter values, right? Now, manually checking all possible hyperparameter values is next to impossible because it is extremely difficult. So your neural network may have 5 layers, may have 150 layers, right? So you cannot check each and every hyperparameters at once, right? And that will be computationally complex. Now, the goal of NAS is that it will give you an automated approach to find out a suitable network for the task. Now, here our task is related to NAS for transfer learning. So in transfer learning, what we do, suppose this is a given network which is trained in some other domain. Okay, say for image classification, that is a very big network. So for example, here the network that we are showing, this is actually AlexNet. Okay, anyway, it can be any CNN. Now you train the CNN on any large data set and you want to apply on your target data set, right? Using transfer learning. Now, what usually people do is that after this structure, after this CNN structure, while applying on the target dataset, you add some more CNN layers, say 3 or 4 more CNN layers, and some 3 or 4 more fully connected layers, and then classification layers, right? Now, while training on the target dataset, you freeze the learned knowledge acquired by this main network, and you only fine tune the new layers that you have added to it, right? That is transfer learning. Now start with a pre-trained large network. Keep on changing the hyperparameter values. How many new CNN layers will be there? How many new fully connected layers will be there? You don't know, right? These are the hyperparameter values. Now keep on changing. Yes. Okay. So the idea is that start with a sufficiently large neural network, right? Say, for example, 10 CNN layers you are adding and followed by 5 fully connected layers you are adding, right? Sufficiently large. Now keep on changing the hyperparameter values at each step. Now, how to do that? Take up some candidate hyperparameter values. Say, fix up some range for the hyperparameter values. Say, for example, you will try with number of layers from 3 to 10, right? And for each layer, the number of neurons you want to keep from 5 to 10. Okay, so these are the possible hyperparameter values. Now take a candidate value for each of the hyperparameter, right? Now how these candidate values of the hyperparameters will be taken at random? Certainly not, because that will not help. So for that, we use a mathematical function, which is called surrogate model. A surrogate model, that is a mathematical function, which is used to cleverly find out the next possible hyperparameter values, right? Now, there must be some optimization function, and in our case, the optimization function may be validation accuracy. So whatever hyperparameter value will give you better validation accuracy, you will take that. As simple as that, right? So this is the idea. So this is the overall approach for any NAS method. There is a search space, as I told, the set of all possible hyperparameter values. Say, for example, number of neurons may be 5 to 10. Okay, number of layers may be 3 to 10 or whatever. Learning rate may be starting from say 0.001 to 0.01. Right? Just saying, these are some examples of search spaces. Right? Now, from these search spaces, your search strategy will pick up a set of hyperparameter values. That is your architecture. Now you train the architecture and test the performance. Right? Now you take the feedback of performance and your search strategy will pick up the next set of hyperparameter values from search space. Right? With the use of surrogate function. So these are some popular strategies, search strategies. First two are older strategies. Nowadays, people don't use them. One is grid search. I think in your study, in many areas in algorithms and so on, you saw these kind of methods, grid search. Suppose your hyperparameter values, one hyperparameter value may range from 3 to 10. Another hyperparameter values may range from 5 to 10. So your row will contain 3 to 10, column will contain 5 to 10, right? And you try
Yes.
on each of them, right? That is grid search. Another is random search. So certainly these are not very good methods. Now comes, the modern methods are actually using these 4 methods. One is evolutionary methods. Another is reinforcement learning methods, another is gradient-based method, another is Bayesian optimization methods. Actually, it depends upon the name depends upon what surrogate function you are using. If your surrogate function is based upon evolutionary methods, then it is evolutionary based NAS. If your surrogate function is depending upon reinforcement learning method, then it is reinforcement learning based search strategy, and so on. So here we'll use a search strategy which is Bayesian optimization based. Now, the main advantage in Bayesian optimization is that the number of parameters are needed is much lesser compared to evolutionary methods or reinforcement learning methods. Here, number of operations or number of memory usage are more. Okay, but in Bayesian optimization, the number of memory usage is much lesser. So first of all, in Bayesian optimization, we build a surrogate model of the objective function based on Bayesian probability. Yes, Sudhan?
Yes, sir. Sir, I have a doubt. Sir, for neural architecture search, it usually required a lot of experiments and resources. But
Exactly.
as a student, we don't have access to that much. To what is a simple way to try out hyperparameter?
Yeah. So this is actually a method for trying out hyperparameter values with some, you can say, some mathematical approach, so that you don't have to try with many hyperparameters, right? So you first start with a set of hyperparameter values, check with that, take the result, and based on the result, your surrogate model will see, or it will figure out that what may be the better set of hyperparameter values for the next iteration. Right? So it is not taking hyperparameter values as at random. Right?
Okay, sir.
So that is the main idea of NAS.
Yes, sir.
So use it to select the most promising hyperparameters, the surrogate model, test on the true objective function. In our case, the objective function is validation accuracy. We have to maximize it and update the hyperparameter values and repeat. So this is the process for Bayesian optimization based model, NAS method. Now, how a surrogate function look like, or how to build up a surrogate model? So for that, we need to first learn about selection function. What is selection function? This is a criteria to choose the next set of hyperparameters. So this is based upon expected improvement. What is expected improvement? Improvement of X. X is a set of hyperparameter values. Expected improvement for a set of particular set of hyperparameter values is equal to this one. So don't get scared by the mathematical equation. I'm just telling you that here y star is just a threshold on y, and y is the objective function, the validation accuracy, right? So you are just specifying some threshold on the validation accuracy, that we want validation accuracy greater than 95%. Otherwise, we will not take it, right? Now, probability of y given x. What is that? X is the hyperparameter values and y is the objective function value, right? Now, this probability will give you that given the hyperparameter values, what is the probability that your objective function value is greater than this, right? If this probability is higher, then you will take it. Otherwise, you don't take this x as hyperparameter values, right? So this is your selection strategy. Now, getting the value of probability of y by x is difficult. Okay, because we don't know what will be our validation accuracy if we take these particular set of hyperparameter values. But the other way, it is much easier. If it is given that the the validation accuracy is 95%, then or maybe some validation accuracy we already got, then what is the hyperparameter value? Okay, that is much easier to determine. Okay, so we apply Bayesian rule that P of y by x, y given x, equals to P of x given y into P of y by P of x. Now, P of x means x is the hyperparameter values, which is fixed. So P of x is a constant, right? So in this case, it will only depend upon the P of x by y. Now, P of x by y is chosen in this way. It will give a very low value, L of x, if y is less than the threshold, if validation accuracy is very less, and it will give a higher value if validation accuracy is higher than the threshold. This is Bayesian optimization, right? Now, we did a little modification over this. Instead of just taking LX and GX, that means only yes or no kind of things, right? Either a very high value or a very low value. Yes, please.
Yes, sir. I also had a doubt. So recently, for a project of mine, I have been reading over Bayesian theory. What would you say its practical applications in today's world is?
Yes.
Like, where is it used and where can it be used?
Yeah, this is one example of the use of Bayesian Bayesian rule, right? Say in this case, you can see P of y by x is not possible to calculate in this case. So what we do, but you have to maximize it. So what we have to do, we have to apply Bayes rule to say that P of y by x equals to P of x by y into P of y by Px. So in that case, P of x by y is easier to identify rather than Py by x. Right?
Yes.
Okay. Now, instead of giving a higher value or lower value, in this case, what we are doing is that we give some continuous value, say some proportion or some constant into Lx by Gx. That is your P of x by y. So instead of getting either high or low, means either 1 or 0 value, you are getting some intermediate values. Okay, some continuous values. Right? So that gives much better result compared to the traditional Bayesian optimization. Okay. Now, to handle less data, what we do is that, first of all, apply NAS on transfer learning so that for target area or target domain, you can apply the idea. Another is that apply NAS on self-supervised architecture. As I told before, self-supervised architecture means you don't need the label data. So you don't have to annotate in this case. So annotate the time for or manual labor for annotation is minimized in this case. Okay, so this is a typical self-supervised model where you learn to, you learn the contrast. Okay, so here dog image and dog image are together, but dog image and bird image are apart. Okay, so same kind of images will attract and different kind of images will repel. So that is the idea of self-supervised model. Now, how to apply NAS on this? So in first step, what we do is that we only tune the number of fully connected layers and freeze the CNN layers and all the others, other layers. Okay. So this was the result that we got. So blue is the result given by our method on CFAR 100 dataset. Now, after that, we made another experiment where we, instead of only fully connected layers, we go ahead for CNN layers as well. Okay. And freeze the other layers. So in that case, the results are much better. Okay. So this yellow is the earlier approach of only fully connected layers, and blue is the newer approach of other layers. Now here we observed one thing. These are the effects of different hyperparameter values. And these hyperparameter values are quite similar. Okay, for this particular hyperparameter value, we are getting the highest accuracy, that is true. But for the other hyperparameter values, the values are not that much less. Okay, the values don't vary a lot. Number of CNN layers, number of fully connected layers, number of neurons, number of kernel size, we tested individually. But their influence on the overall accuracy is much less rather than learning rate. Learning rate actually matters a lot. Okay, so these two, first one and second one, are on CFAR 10 and CFAR 100 datasets. These are smaller datasets. But third one is on ImageNet dataset. That is a larger dataset. And we can see that it is much more prominent in larger dataset. So for larger dataset, learning rate plays a big role for any neural network. So that is one idea that we got from our experiment. Now, next idea that we proposed is that removing the last CNN layer, the last CNN layer of the main self-supervised model. Okay, so as of now, what we are doing, we are only engineering on the new layers that we are adding during transfer learning. But here, what we are doing, we are now entering into the main network. Okay, and we remove the last layer. So it will actually reduce a huge number of parameters, and that actually enhances the result drastically. Okay, so we did some more experiment. One is applying knowledge distillation. The knowledge distillation means suppose you want to apply your algorithm on a specific task which has smaller data set. Now, what you will do for smaller data set, you can only apply smaller network, right? Otherwise, it will overfit. Now, suppose, but these smaller networks may not give you a very good result. So what you will do, you come up with a large network. That is the teacher model. The idea is that the teacher knows many things. So it is trained on several other things, but it is not focused towards a particular task, right? But the student is introduced with a particular task. The student will learn the knowledge from the teacher and apply to the particular task. That is the idea of knowledge distillation. So there will be a teacher model and a student model. Teacher model is a larger one, student model is a smaller one, right? So you train the smaller model on the target data where you learn the knowledge from the teacher model. So this is called knowledge distillation. And here we applied the same knowledge distillation with ensemble model. So what is ensemble model? Ensemble model means it is a, we are just concatenating the result of several CNNs. Instead of one CNN, we are taking several CNN models and taking a combination of them. That is our teacher model. And we apply with the student. Okay, so what are the other ideas that we can think of from this research? Can we prune out some unnecessary layers? So as of now, we are talking about hyperparameter values. What will be the number of layers? But can we delete some layers if these layers are not that much useful in training, right? Can we prune out some unnecessary units? Units means neurons. Some particular neurons. For several epochs, if some particular neurons are not changing the values, right? So can we prune out them? So these are some new areas that are coming up. And okay. Now, these are some possible extensions of this work. So as of now, now people are thinking more about explainability. So you apply a deep learning model and it is working very well. This is not enough. Suppose if you want to detect whether a patient has brain tumor or not, this is a very crucial thing. Okay, so you cannot just rely upon some technique which is not foolproof. You don't know whether it is really focusing on the tumor area or not. So people are more interested towards explainability of the model, how it is doing. Okay, it is giving 95% accuracy. We understand that. But is it really focusing on the brain tumor area? So this is the question that people are asking nowadays. So there are several approaches that people are trying to apply. One is the mathematics behind deep learning. How deep learning really works? Can we mathematically model the information flow? How the information is flowing from one layer to another layer and so on in a deep learning model during training. So one person that I have named here, Rene Vidal, you can just go to his website of Johns Hopkins University. So you will learn many things. He works in this particular area and he is maintaining his web page very well. So you can just search with that. And he has several lectures on this topic. Another idea is information bottleneck theory, given by Naftali Tisby of Hebrew University, Jerusalem. So this is another idea. Information bottleneck theory is actually a theory from signal processing area. This is actually a probabilistic theory. Now, he shown that this probabilistic theory can be applied on deep learning models to predict the information flow from one layer to another layer. Okay, so this is another area that people are now working on. Another area is gestaltism. So Gestalt theory is a popular German philosophical theory, actually. Now, Agnes Disselniaks is working on this area that can we apply Gestalt philosophical theory and come up with a mathematical model or probabilistic model on this theory. Actually, Gestaltism says that how can we predict or how can we recognize a chair, for example? The chair can be of different kind of shapes. In some chairs, there will be only one leg. In some chairs, there may be 4 legs and so on. But anyway, it is a chair. We can identify it as a chair. How can we do that? Now, according to Gestalt theory, it says that human brain, when human brain looks at some object, it actually cuts down the object into several pieces and try to bring them together to form a meaningful structure. And that structure actually explains everything for the human brain. That is the Gestaltism. Now, can we apply the Gestalt philosophical theory into this explainability of deep learning? Okay, so that is another area that people are, Agnes Disselniaks, she is actually working in this area, Paris University. Now, another possible extension that can be done from here is that neural architecture design. So this is actually an idea which is proposed only in this year, 2025. 1 or 2 papers came in ICML conference, which is the topmost conference in machine learning, where, so as of now, what we are doing, our model just takes some possible hyperparameter values from your search space. Okay, and we are starting with a bigger model and we are gradually shrinking our model to come up with a smaller model. That is the idea of NAS. Neural architecture design is a two-way solution. If possible or if required, we can expand our network, or if required, we can squeeze our network. Okay, both way it is possible. Now people are applying LLMs to come up with such neural architecture design methods. So this is a new area of interest that is coming up in future. Okay, so I'll stop here for any question. Thank you.
So I had one question.
Yes.
So you mentioned the possibilities about this. I would also ask you when have like an example where you have used such techniques in your projects.
I could not understand. Can you please repeat?
Uh, so how did you apply such techniques in some projects which you have done, such as one project in your egocentric activity recognition?
Okay, so for egocentric activity recognition, I have not applied NAS. Okay, so for egocentric activity recognition, it is a completely different topic. I came up with some deep learning models which work on the motion analysis part, and another model which concentrate on uh, the spatial analysis part. Spatial means at frame by frame analysis part. Okay, and we combine these two. So that is the overall approach for any video processing task. Okay, so so that is a completely different area, and that requires a different kind of. It may be a different lectures also altogether.
Okay, sir.
Okay. So I think another question is there, Shriya.
Yes, sir. So, when we say that we are training our model with limited data, so is there any threshold of data which is required for a model to remain reliable? Like, how can we identify whether the data we have, though it is limited, whether it is truly, like, can we make a model and which will be reliable, or we should seek for more data?
It's a very good question. Actually, uh, suppose if you have an application area, and if you ask me exactly how many images you need to train a model in this area, I have no answer for that. And nobody can have any answer for this. Uh, Actually, it's very difficult to determine how many images are required. Actually, it depends upon many things. How much is the complexity of the data? Okay, suppose in medical images, in many cases, suppose there is a kind of images called histopathological images, which are used for cancer detection. So if you see those images, you can just search in internet histopathological images. You will see some sample images, and if you see those images, you will understand that how difficult is it to identify the cancerous area, even in our eyes. Only experienced doctors can identify that, okay, there is cancer or not. So how a model will identify? So to identify from such images, you need lot of training, and you need a huge amount of data in those cases. But if the say you have cat image and dog image, you have to separate cat image from dog image. So these are much lesser, uh, I mean, lesser complex problem, right? So in this case, number of required images will be much lesser. Okay, now training with lesser data, this kind of research comes up with the idea that suppose in such an area where getting huge amount of data is not possible. Not possible means not possible. We cannot get. Now with that restriction, how can we come up with an algorithm which will fit, or which will just give us some result which is which we can rely upon. So that is the idea of this kind of research.
Yes, sir. Thank you.
Any other
If
question?
anybody, If anybody else has any doubts, maybe relating to the project they are doing now or something else, or if you cannot unmute, please type your doubts in the chat also. So there's a question on the chat asking which books did you refer?
Okay. For if you want to work in computer vision area, then I would recommend an online course is there. That is Stanford University course. The number is CS231N, N for Nagpur. CS231N. Okay, that online course you can take. So this is a very good course to take you to the research level in computer vision area. Okay, so that is one example. And for more in-depth knowledge on deep learning and related area, I would recommend a very good book that is freely available online. That is Deep Learning book by Ian Goodfellow, MIT Press. So that is freely available. If you just search by the name Deep Learning Ian Goodfellow, just with this, you can search in Google, you will get it from MIT website. That is a very good book. Chris, you are muted. Okay, Sarang? Yes?
Hello.
Uh-huh.
Sir, how to actually decide the features while data pre-processing and cleaning? Like basically, we have given a task before, and we have to create that models for it. But how to select that these all features are actually making this good? Like for cleaning, it is the most important part, right? For making the model.
Okay. So I'll answer it in this way. There are two kinds of feature engineering. Okay. So one is that before deep learning methods came, what we used to do is that we used to come up with a mathematical model so that with our intuition and whatever experience and whatever, we used to come up with a mathematical model which will give you the feature. So this is called representation of the image. Suppose you have an image. Now you have to represent the image in such a way that any machine learning technique can predict or classify or whatever, right? Now this is called feature representation. Now how to represent this image with a set of numbers? So that will be given by some mathematical model. What is the model? That is the kind of research that we used to do before deep learning model came. After deep learning model, the research direction is completely changed. Okay, completely changed means now the feature representation is done by deep learning model blindly. Okay, so if you give an image, it will just go by the pixel intensity values of the images. Okay, and it will come up with some feature representation after some layers, right? So that is done by deep learning model, and the kind of feature representation that it gives, that is far better than the mathematical model that you will come up with, right? So so to answer your question, the feature representation is nowadays actually done by deep learning models. But before that, there have been some more areas, some more techniques, say, for example, PCA, principal component analysis. Okay, so I am not going into the details of that. So these are some methods that will give you that which features are more useful for these kind of tasks.
Yes,
Okay, Suhani.
Hello.
Yes.
Sir, I had a doubt. Like many a times we are working on images which do not have a good resolution, but yet we have to extract minor features. So what can be used in such cases?
Okay, so there is a popular research area which is called super resolution. Given a low resolution image, can we enhance the resolution of the image without distorting the actual content of the image? Okay, that is called super resolution. So that is a separate area of research. Now, if you want to say that, okay, how can we apply some image analysis technique on low resolution images? Then one idea is that you can make it a high resolution image and then apply your algorithm. That is one task, but that is memory. If the memory overhead will be very high in that case, because image resolution, super resolution is a technique which requires lot of computation power. And then you are applying your algorithm, image analysis algorithm. Okay. Now there are some research methods. Say for example, mm, so actually it's difficult to tell in few minutes. I would suggest you that you go through the book that is also freely available online, Richard Zelinsky. Okay, or Rick Zelinsky, Richard Zelinsky or Rick Zelinsky. Okay, he has a computer vision book, so you can go through it. You will see a different chapter on this. Working with low resolution images, how we can deal with it.
Okay, sir.
Okay.
So, on behalf of the PICT ACM Student Chapter, I would like to extend our sincerest gratitude to Dr. Snehasis Mukherjee for the incredibly insightful presentation and session. I hope all the people who attended could learn something new about computer vision and machine learning and how to train using the different techniques. Uh, Thank you so much, sir, to help the second year students who are just beginning to explore the vast field of AI. Thank you for taking time out of your busy schedule and share your expertise and inspire us. We are immensely grateful for this opportunity and wish you the best in your future research and hope to have the opportunity to collaborate again. And thank you everybody for joining.
Thank you for inviting. So yeah, and best wishes to all of you.
Thank you, sir. Now everybody can leave the meeting and the session has ended.
Yes.